In this video, I'm going to show you how to solve improper integrals. As you can see, this integral here is improper because it has an infinity on the integral sign. So how do you solve these? Well, first things first. An integral is called convergent if you solve this and you get a number as the answer. So let's say you solve this and you get 1 as the answer, or 2 or 3, then this integral is called convergent. And if you solve this and you get the answer as infinity, then it means that this integral is divergent. The first step is to convert this into a limit. So this integral is equal to the limit as t approaches infinity of the integral from 1 to t of 1 over x to the power of 2 dx. So as you can see, here we're basically saying that as t approaches infinity, then this part will be infinity. So it's basically the same thing. Now, using the second fundamental theorem of calculus, we can rewrite this as the limit as t approaches infinity of f of t minus f of 1, according to the first or the second fundamental theorem of calculus, where f of t, or f of x, is equal to the integral of 1 over x to the power of 2 dx. The integral of 1 over x squared dx can be rewritten as the integral of x to the power of minus 2 dx, and the antiderivative of that would be x to the power of negative 1 over negative 1 plus c, which is the same as negative 1 over x plus c. We found the antiderivative, f of x. So what is f of 1? So f of 1 will be equal to negative 1 over 1 plus c. But we don't need to write out the plus c because this is the antiderivative, right? So f of 1 will just be equal to negative 1. And for f of t, we have f of t that's going to be equal to negative 1 over t. We found out these two values. Let's go ahead and put them back into this limit. So this is equal to the limit as t approaches infinity of minus 1 over t plus 1. So the function negative 1 over t looks something like this. So if we have this function and we graph it, it's going to look like this, where this right here is the t-axis and this is the y-axis. As t approaches infinity, so as t approaches infinity over here, you can see that this function approaches 0. So that's why this is equal to just 0 plus 1, which gives you 1. And that is the answer to this integral. Since it gives you a real number as the answer, we know that this integral is convergent. How about the integral from 1 to infinity of 1 over x dx? So just looking at this right away, I can tell that this is divergent. There is a trick, which I'm going to show you in a second, but for now, let's just solve it the normal way. So this integral is equal to the limit as t approaches infinity. And you don't have to use t, you can use any variable, but t is the most common in textbook. You get the integral from 1 to t of 1 over x dx. And then we can use the second fundamental theorem of calculus, and we get the limit as t approaches infinity of f of t minus f of 1. The antiderivative f of x will be equal to the integral of 1 over x dx. So the antiderivative of this is just ln x plus c. So we found f of x. What is f of t and what is f of 1? Well, let's see. So f of t will just be ln of t, and then f of 1 will be equal to ln of 1. And what is the ln of 1? Well, that is going to be equal to 0. So we can simplify this into the limit as t approaches infinity of ln at t. So if you graph this as t approaches infinity, if you graph this where this is the y-axis and this is the t-axis, you will get a function looking like this. and that is ln at absolute value of t. As t approaches infinity, this function will continue to go up and up and up, which means that this function also approaches infinity. So the limit is equal to infinity. And because you get infinity as the answer, we know that this integral is divergent. So here is the formula. Whenever you see the integral from 1 to infinity of 1 over x to the power of p dx, so if p is larger than 1, then this integral will be convergent. And if it is smaller or equal to 1, then it will be divergent. Now it's your turn. We have an integral from negative infinity to 0 of x times e to the power of x dx. So feel free to pause this video and try this, and then we'll go over the solution together. Okay, so this is going to be the same as the limit from t to negative infinity of the integral from t to 0 of x times e to the power of x dx, which is equal to the limit as t approaches negative infinity of f of 0 minus f of t. Now f of x, so f of x, will be equal to the integral of x times e to the power of x dx. So we have to use integration by parts, and the formula for integration by parts is u dv is equal to u times v minus the integral of v times du. And we have to use the Liat rule, where L is logs, I is inverse tricks, A is algebra, T is trig, and E is exponential. So as you can see here, we have x, and x is the algebra right there. And then we have e to the power of x, and that would be the exponential. So because the x comes first, that would be our u. So let me show you what I mean. So we have let u is equal to x, which means that du over dx is equal to 1, which means that du is equal to dx. So that is the u part. For the dv part is the rest of everything we have in the integral. So dv is e to the power of x dx, which means v is the integral of that. So e to the power of x dx, which is simply e to the power of x. So using this integration by parts, we get x times e to the power of x minus the integral of v, and v is e to the power of x, so e to the power of x dx, which is simply x times e to the power of x minus e to the power of x plus c. What is f of 0 and what is f of t? Well, let's find out together. So f at 0 will be 0 times e to the power of 0 minus e to the power of 0. And this would just be 0 minus 1, which is negative 1. For f of t, it will be t times e to the power of t minus e to the power of t. So using what we have, we should put it back into our limit. Continuing on, we have the limit as t approaches negative infinity of negative 1 minus t times e to the power of t plus e to the power of t. And then what we can do now is split this limit apart. So this is going to be equal to the limit as t approaches negative infinity of minus 1 minus the limit as t approaches negative infinity of t times e to the power of t plus the limit as t approaches negative infinity of e to the power of t. We know that this limit will be negative 1 because no matter what t approaches, this will always be negative 1. So this is negative 1, and over here, what would this one be? Well, e to the power of t, the graph will look something like this, right? That's e to the power of t. So as t approaches negative infinity, so as it's approaching over here, the graph goes to 0. So this limit will be 0. In fact, we don't even need to write the plus 0, so we can just take it out. How about this one in the middle? Well, as t approaches negative infinity, the t will become the negative infinity. And as t approaches negative infinity, the e to the power of t will be 0, right? So we have this indeterminate form, which means we can use L'Hopital's rule. So let me go over L'Hopital's rule very quickly for this case. In fact, this can be plus or minus infinity times 0. Then the limit as t approaches any number of f times g can be rewritten as the limit as t approaches any value of f over 1 over g, or the limit as t approaches a of g over 1 over f. The second case scenario for L'Hopital's rule is if you have infinity over plus or minus infinity, or you get 0 over 0. So in this case, you can rewrite the limit as t approaches a of f over g as the limit as t approaches a of the derivative of f over the derivative of g. So you just differentiate the numerator and the denominator. For this case, for this limit, we're going to use the first rule. This limit right here is equal to the limit as e approaches negative infinity of t over 1 over e to the power of t. So instead of writing like this does not look beautiful. So you can make it easier for yourself and write this as e to the power of negative t. Now, if you look at this will give you infinity over infinity. Now, why is that? Because as t approaches negative infinity, this t approaches negative infinity. And as t approaches negative infinity, this down here will be infinity, because this graph looks something like this, right? That's the graph of e to the power of negative t. So that will give you infinity, and because of that, you have to use the second rule for L'Hopital's. We simply differentiate the t and we get 1. And for the denominator, what is the derivative of e to the power of negative t? Well, this would simply be negative e to the power of negative t. So up here, this is 1 over negative e to the power of negative t. And we're close to finishing this limit. So this limit is equal to the limit as t approaches negative infinity. And then there's the minus sign because of this, the minus sign of 1 over e to the power of t. When you divide by a number that's 1 over e to the power of t, you will simply get e to the power of t. So this will be negative e to the power of t. So what does this graph look like? It's going to look something like this. And because of that, when t approaches negative infinity, this graph approaches 0, which means that this limit is going to be equal to 0. That also means that this limit is 0. And negative 1 plus 0 is just negative 1. So this is the answer to the integral. And because it is a number, then we know that this integral is convergent. How about the integral from negative infinity to positive infinity of 1 over x squared plus 1? Well, one formula you should know is that when you get something like this, you can always split up the integral into the negative infinity to a, where a can be any number, and plus the integral from a to infinity of f of x dx. So using this formula will really simplify your work and make you finish this faster. So this is equal to the integral from negative infinity, and you can choose any number up here. I'm just going to choose 0 of 1 over x squared plus 1 dx, plus the integral from 0 to positive infinity of the same function. The first thing I'm going to do is solve for this one, and then afterwards we'll solve for this one. We can rewrite this as a limit, so the limit as t approaches negative infinity of the integral from t to 0 of 1 over x squared plus 1 dx. This is the same as the limit as t approaches negative infinity of f of 0 minus f of t. So the antiderivative f of x will be the integral from 1 over x to the power of 2 plus 1 dx. And you should know that this is equal to arctan of x plus c. So f of 0 will be equal to the arctan of 0, which is 0, And f of t will simply be the arctan of t. So we can put these values back into our limit, and we can get negative arctan because we no longer need the 0. And remember that you can always move this negative sign outside to the limit. So let's go ahead and do that. So what is the graph of arctan? It is going to look something like this, where this is t, this is y, and there is a horizontal asymptote here of pi over 2. And down here, there is an asymptote of negative pi over 2. So this graph will never exceed this line or exceed this line below. And because of that, as t approaches negative infinity over here, we know that it is going to approach negative pi over 2. So this integral will produce pi over 2. So if you solve this one over here, and let me save you some work, if you solve this one, you will also get pi over 2. And pi over 2 plus pi over 2 will give you pi. So pi is the answer to this integral, and therefore we know that this is convergent. Let me tell you something. This integral is also improper, and it is a special case of improper integrals. The reason is that you see that when x is equal to 2, then the denominator will be 0, so it will be divided by 0, right? So whenever you see that there is a value between here and here that makes it divide by 0, then this is also improper. The first thing I'm going to do is draw out the graph. So the graph of this function, it will look like this, where this value is 2, there is an asymptote here, and this is a 5. So the way we solve this is exactly the same as the way we've done it before, which is to use a limit. So the limit as t approaches 2 from the right side, okay? We're approaching this from the right side, therefore there's a plus sign here, of the integral from t to 5 of 1 over the square root of x minus 2 dx. And we can also use the second fundamental theorem of calculus. We get t approaches to from the right side of f of 5 minus f of t. We need to find the antiderivative. So f of x is equal to the antiderivative or the integral from 1 over the square root of x minus 2 dx, which is the same as the integral of 1 over x minus 2 to the power of 1 over 2 dx. Let u equal to x minus 2, so du over dx is equal to 1, and du is equal to dx. This integral will be the same as 1 over u to the power of 1 over 2 of du, which is equal to the integral of u to the power of negative 1 over 2 du, which is equal to the antiderivative of this. So u to the power of 1 over 2 divided by 1 over 2 plus c. And this gives us 2 times u to the power of 1 over 2 plus c. And we have to substitute u with x minus 2 with our original variable. So 2 times x minus 2 to the power of 1 over 2 plus c. What is f at 5? Well, f at 5 will be 2 times 5 minus 2, which is 3 to the power of 1 over 2. And we can write this as 2 and the square root of 3. And f at t, so f at t will be 2 times t minus 2 to the power of 1 over 2. And let's go ahead and put these values into our limit. Finally, as t approaches 2, we can just go ahead and plug it into here. We get 2 the square root of 3 minus 2 times 2 minus 2 to the power of 1 over 2. This is equal to 2 the square root of 3 minus 2 times 0. So we get 2 and the square root of 3. And this is our answer. And because it is a number, then this integral is convergent. How about the integral from 0 to 3 of 1 over x minus 1 dx? Well, this is improper because between 0 and 3, when x is equal to 1, then this will be divided by 0. And that's why this integral is improper. we're going to split this integral apart. So we get the integral from 0 to 1 of 1 over x minus 1 dx plus from 1 to 3 of 1 over x minus 1 dx. So we will solve for this one first. This is equal to the limit as t approaches 1, but from the left side. So we get a minus right there. And then we get the integral from 0 to t of 1 over x minus 1 dx, which is equal to the limit as t approaches 1 from the left side of f of t minus f of 0. f of x will be the integral of 1 over x minus 1 dx. And we're going to use u substitution here. So let u equal to x minus 1. du over dx will be equal to 1. So du will be equal to dx. And last but not least, we're going to get ln u plus c, which is equal to ln of x minus 1 plus c. So what is f of t? Well, f of t would be ln of t minus 1, and f of 0 will be ln of 0 minus 1. That's going to give us ln at -1. But since this is an absolute value, then we get ln of +1. And remember, the ln of +1 is just 0. So f of 0 will give us 0. We get the limit as t approaches 1 from the left side of ln of the absolute value of t minus 1. And then we can close the bracket right there. So if you look at this, when t is 1, okay, it doesn't matter if it's approaching from the right side or the left side. When t is 1, then this in here will be 0 because 1 minus 1 is 0. You need to know that ln of 0 is -infinity. And because of that, this limit will be equal to -infinity. So we found out that this one is -infinity, which means that this integral is divergent. And whenever you split the two integrals and you find out that one of them is divergent, it means that the whole thing is divergent. So the answer to this question for this integral is -infinity. And because of that, we know that this integral is divergent. That's basically it for today. I know that's a lot of information to take in from just one video, but I hope you enjoyed it and I hope that you learned a lot of things from this video. Now, if you enjoy it, make sure to hit that like and subscribe button, and don't forget to comment if you have any questions. So for homework, maybe this question will be on a test. You might get something like this. So you might get the integral from 0 to 1 of ln x dx. So this might go on a test, and I'll leave it as a homework problem. If you solve this, you should get -1, and because of that, you know that this integral is convergent.